Right, so let's talk about electronic transition in transition complexes. So basically, when a metal absorbs sufficient energies, their valence electrons are transitioned from a lower to a higher energy level to produce absorption spectra rather. So let's say we have Fe2 plus. So basically, Fe is ion is 26, right? So the configuration is basically Fe2 plus is we have it to be Ar 4s2 and 3d6. So the this for this. So but for this we have it to be Ar 4s0 3d6. So this is the configuration, right? We have, let's say this is a tetra octahedral in an octahedral complex. So let's say for octahedra we're going to have this, right? So we have this. So the 6 electrons fill in like this: 2, 3, 4, 5, 6. So this is the 2G and this is the Eg. So basically, this electron here can actually transition to higher energy level when sufficient amount of energy is absorbed. So when they lose electron also, emission spectra occurs. So basically, this is absorption spectra, right? Moving from a lower energy to a higher energy, right? So an emission is basically moving from a higher energy to a lower energy level. So basically, electron transitions between energy levels are governed by two rules. So the first rule is spin selection rule, and the second is LaPorte rule. So let's look at the spin selection rule. So the spin selection rule states that the change in spin must be zero, right? So this means that during transition, electrons retain their spin. So in the case of iron 2 plus the other time, we said we have this, right? So this, and this. And so this is the last electron. This is the last electron. So if this one should transition to a higher energy level, it must retain its spin. So we can't have this. We can't have this. So this is this. So this last electron cannot come here to become this. So it's impossible. So basically, this kind of transition is not possible. So it has to be downwards also. So basically, electrons retain their spin both in magnitude and direction. So this spin is negative 1 over 2, right? So transitions involving same multiplicity are allowed. Those with different multiplicity are not allowed. So looking at this, so this is the multiplicity, right? So spin gives rise to multiplicity, right? So basically, if the spin is the same, or if the multiplicity is the same, then the transition in spin allowed. So looking at this also, the multiplicity is the same, so it's allowed. But looking at this, the multiplicity is not the same, so this is not allowed based on the spin selection rule. So also looking at the LaPorte rule. So the second rule is the LaPorte rule. So the LaPorte rule states that the change in L must be positive or negative 1. So this means that transitions involving change in polarity, no change in polarity rather, is forbidden. So the positive, it can be positive 1 or can be negative 1. This means it can move from like S to P. It can also move like from P to S, right? So looking at this, the change in L is basically 1. No, the L value for this is 0, but this is 1. So the change in L is basically positive 1. So this is allowed. This is also allowed. So this is moving downward. This is also allowed. D to F is also allowed. Now looking at this, we have S, P, D, and F, right? Let's put G also. So we have this to be 0, 1, 2, 3, and 4. So basically, in this case, we are moving from S to D. So that is basically forbidden. That's forbidden because the change in L is positive to right. It's greater than 1. So now let's look at DD transition. Although looking at the LaPorte rule, we might want to say that DD transition is actually forbidden because the change in L is basically 0, right? But there are some conditions that make this DD transition possible. So DD transition is also possible on some cases. So let's look at it. So basically, DD transition have the same parity but are still observed due to one. So the first reason is the mixing of states, right? And the second one is the Vibronic coupling. So the mixing of states where we have spin orbit coupling, right? And the second reason is this Vibronic coupling. So you just need to know these two. These are the reasons why this DD transition is possible, despite the fact that the change in L is 0. So now let's look at this question. So which of the complexes has a spin allowed transition for its configuration, for its electronic transition? So basically, the first thing you need to do is to calculate the oxidation number, right? So looking at this, we have this to be Mn plus 6 into bracket of 0 to give plus 2. So we have this Mn to be plus 2. So the configuration for Mn is basically we have AR, we have 4s2 and 3d5. So basically we have Mn2 plus to be AR 4s0 3d5. So this is a d5 configuration, right? So let's look at this also. So this is basically CO plus 6 into bracket of 0 to give positive 2. So we have this to be cobalt to be plus 2, right? So cobalt is CO is 27, and that's AR. We have 4s2 and we have 3d7. So CO 2 plus is basically AR. We have 4s0 3d7, right? So now the next thing we need to do is since the question says which of the complexes has a spin allowed transition for its electronic transition. So now let's find the ground term for this. So basically this is this. Okay, without looking at the ground term, let's just do this, right? So this is d5 and this is octahedral, right? So this is Eg and this is T2G, right? So we have 5 electrons. So 1, 2, 3, 4, 5. So for this also, let's look at it. So we have it to be D7. So that is going to be so we have T2G and we have Eg. So this is 1, 2, 3, 4, 5, 6, 7. Right? So looking at this, if you are going to transition an electron from this lower energy to this higher energy, with the spin change, we are looking at spin allowed transition. So spin allowed transition states that change in S is 0. That is, spin does not change in magnitude and also in direction, right? So looking at this is halfly filled, right? So we are going to move this from here down to this point. So for you, it's going to be this. We are going to have at the top this, and this. So basically, this transition is not possible because it violates the onto, right? So for this, let's say looking at this in this case, we can basically transition this last electron here can as well go up there to become this, right? 1, 2, 3, 4. So this last electron can transition can transition to this point. So this one has moved here, right? So this kind of transition is possible because it retained its direction as well. So looking at that, so another way to do this is to calculate the ground term, and then you look from the ground term as well.